This is the video lecture for section 7.1, which is entitled The Central Limit Theorem for Sample Means. In previous videos, we were talking about the probability that an individual value falls on an interval in a normal distribution. In this section, we're going to be looking at the probability that the sample mean falls on a particular interval. So in the same way that the individuals can vary in a population, the sample means will vary depending on the sample that you gather. If you were to gather two random samples, there's a really good chance that the mean that you get for each sample will be different. So the sample means can vary from sample to sample. And what we want to do is look at the distribution of those sample means in order to find these probabilities. Before we get too abstract, let me show you an example of a problem we'd like to be able to do, but we're not quite equipped to do so yet. Women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Find the probability that a random sample of 10 women has a mean height above 65 inches. Now in a casual read-through, that sounds exactly like the kind of problems we were doing before. But the difference is that this problem is not about individual women. It says find the probability that a random sample of 10 women has a mean height above 65 inches. So here we're not looking at the probability that an individual woman is taller than 65 inches. That we already know how to do. Here we're looking for the probability that a sample of 10 women has a mean height above 65 inches, and that's going to require a little bit of new knowledge before we can proceed. And what exactly do we have to know? Well, we have to know the distribution of the means. We know the distribution of the individuals is a bell curve, but if the distribution of the means isn't also a bell curve, then we'll be stuck, because the only continuous distribution we really know how to work with is the normal distribution. We also need to know the mean and the standard deviation of the distribution of the means. Well, it turns out that we can determine all of those things. We can determine the distribution of the means, we can find the mean of the means, and we can find the standard deviation of the means. To prove any of those characteristics would be beyond the scope of our course, so I'm just going to present them as facts. So let's consider all possible samples of a given size, which we'll call n, taken from a normally distributed population with a given mean mu and a given standard deviation sigma. That's the exact scenario we have in our problem. We know that the variable is normally distributed, we know its mean, and we know its standard deviation. So we're going to consider any generic example like that. Here are the three facts that we need. The mean of all of the sample means from those samples will be the same as the mean of the population. So the mean of the sample means is equal to the mean of the population. And again, while I can't prove this to you, I hope that this is kind of intuitive, that if you were to gather all possible samples and find the mean of all of those samples, well, some of those sample means will be smaller than the population mean and some will be bigger, and they'll balance out to exactly the population mean. It turns out the standard deviation of the sample means is not the same as the standard deviation of the population, though. The standard deviation of the sample means will be the standard deviation of the population divided by the square root of the sample size. So this really says two things. One, the standard deviation of the sample means is smaller than the standard deviation of the population because we wind up dividing by the square root of the sample size. The fact that you divide by the square root of n is something that we could never prove in our class. Some nerd has proven it. This is a fact, but it's beyond our abilities to prove. But I hope it makes sense that the standard deviation of the sample means will be smaller than the standard deviation of the individuals. When you gather a bunch of samples, the means aren't going to vary too much because the individuals in those samples are usually going to balance each other out, and you're going to get something close to the population mean, especially as the sample size gets larger. And that's the second thing that this is saying. Notice that as n gets bigger, this fraction will get smaller and smaller and smaller, which means that you'll have less variation when you have larger sample sizes, which is a mathematical way of saying the bigger your sample size, the more likely it is that your sample mean will be close to your population mean. And the last part deals with the shape. The pattern of variability of the sample means will be a normal distribution. If you know that the original population is normally distributed, then the sample means will also be normally distributed. That's important because we need to know that pattern of variability. If we don't know that it's a normal distribution, we cannot proceed. A little bit of notation that I'm going to work into our pictures. The mean of the sample means is denoted by mu sub x bar. So that first rule that we have on the screen here, that could be rewritten as mu sub x bar equals mu. the mean of the means is equal to the mean of the population. It's hard to tell because I'm not writing between lines, but this little thing is a subscript. So when you read this, you say mu sub, because it's a subscript, x bar. The mean of the sample means. The notation kind of makes sense. So this first line, the mean of the sample means will be mu, just says mu sub x bar is the same thing as mu. The mean of the means is equal to the mean of the population. Similar notation for the standard deviation of the sample means. It's denoted by sigma sub x bar. Again, that's a subscript x bar sitting there. And so we can take that second rule and write it as sigma sub x bar equals sigma divided by the square root of n. The standard deviation of the sample means is equal to the standard deviation of the population, the standard deviation of the individuals, divided by the square root of the sample size. The third rule we don't need to turn into a notation. We're just going to say that if we know the original variable is normal, then the sample means are automatically normal. Let's revisit our example and see if we know enough to do this problem. Women's heights are normally distributed with a mean of 63.6 inches and a standard deviation of 2.5 inches. Find the probability that a random sample of 10 women has a mean height above 65 inches. This is not a question about the individuals. This is a question about the mean of a sample. And so we need to know the distribution of the sample means. Let's go back through our rules. The third rule says the pattern of variability of the sample means will be a normal distribution when we know that the original population is normal. In this problem, we're told that the women's heights are normal, so the sample means are also normal. So I can draw a bell curve. To make it clear in this example that we're talking about the distribution of the means, I'm going to put a little x bar on the end of the horizontal axis. I haven't been putting a label there before because it hasn't mattered. But now to distinguish that we're talking about means, I'm going to put a little x bar on the end. Our usual next step is to put the mean of the variable in the center, but we need the mean of the means, the mean of the x bars, not the mean of the individuals. We're told the mean of the individuals is 63.6. How can we use that? We'll go back to our rules. The mean of the sample means is the same thing as the mean of the individuals. Mu sub x bar is equal to mu. So the number in the middle here, which we would denote by mu sub x bar, is the same as the mean of the population, which is 63.6. Those two things are always the same. The mean of the means is always equal to the mean of the population. How do I know that I need the mean of the means? Because I'm looking at the distribution of the x bars, not the distribution of the individuals. But you can't really screw that up because they're the same. We also need the standard deviation, and that we could mess up. This will not be the same as the standard deviation of the population. Let's go back to the rule. The standard deviation of the sample means will be the standard deviation of the population divided by the square root of the sample size. Sigma sub x bar is equal to sigma divided by the square root of n. This is where it matters how many women there were in the sample. There are 10 women in the sample. So we're going to take the standard deviation of the population, which is 2.5, and divide it by the square root of 10. Now that we know the shape, the mean, and the standard deviation of the x bars, we can answer any question about probabilities that we want to with normal CDF. This is now just like a problem from section 6.2 and how we approach it. We just had to get these three pieces together. We had to know that it was normal, but we knew that because the population was normal. We had to figure out the mean of the means, but that's always just the mean of the population. And we had to find the standard deviation of the means, but that's the standard deviation of the population divided by the square root of the sample size. Now we can answer this question. Find the probability that that mean is above 65? No problem. 65 lives somewhere to the right of the mean. We're going to shade the area to the right of that. This looks like a 0.5 minus problem. We're going to exclude this area right here. So it's 0.5 minus normal CDF, 63.6, comma 65, comma 63.6 again because it always goes in the third spot. And in the last spot, we're going to put 2.5 divided by the square root of 10. I don't think it's worth your time to come up with a decimal approximation and type it into that last spot. You can actually just type this as your standard deviation. I'll show you. Let me bring up my calculator. So I'm going to do 0.5 minus. I hope you can see that it's a minus question. We definitely have less than half of the graph shaded, and we only have this right tail. And we're going to cut out this piece right here that starts at 63.6 and ends at 65. So those are my two bounds. Second vars, choice 2. Oh, I should probably point this out since we just had a video on inverse norm. This is a normal CDF question because we're finding a probability. We use inverse norm to find values of the variable. Here we're finding a probability. That's normal CDF's job. So again, our lower bound is 63.6. Our upper bound is 65, at least for the area that we're subtracting away. The mean is 63.6. And the standard deviation is 2.5 divided by the square root of 10. So I hit second and the x squared key to get my radical. And I just type a 10. And I guess if I want to be careful with the parentheses, I technically have to close twice, once for the radical, once for the normal CDF. But you actually don't have to close either of those. The calculator function will still run. And we get a probability that's about 0.038, or 3.8%. So the probability that 10 women selected at random have a mean height over 65 inches is around 4%. It'd be pretty uncommon. That wouldn't be very likely. If you were to do this for individuals by getting rid of that square root of 10, you'd see that the probability that an individual is over 65 inches tall is almost 30%. It wouldn't be that strange to have an individual woman selected at random be more than 65 inches tall. But if you were to grab a group of 10 women selected at random and find their mean height, it would be pretty uncommon for that mean to be over 65 inches. And that's because what would normally happen is you'd get a few women who are above the mean and a few women who are below the mean, and the average would probably come out pretty close to the mean, 63.6. If you look at the setup, you'll notice it's not much different than if we were doing this for an individual. Really, the only difference is that we have to adjust the standard deviation for the sample size. Okay, so that covers an example where we're told that the original population is normal. But there are lots of scenarios where we don't know the distribution of the original variable, and yet we can still follow this procedure. And that's because of a very important theorem that's called the central limit theorem. Now, what I'm going to present to you isn't the true central limit theorem. It's just the application of the central limit theorem that we'll need. So this is kind of the central limit theorem. It says the sampling distribution of sample means will be normal provided that a sufficiently large sample size is used. Even if the original variable is not normally distributed, right? You've got this variable that's kind of lumpy and not normally distributed at all. This is the original variable, so I'm going to call that x. If you were to look at the distribution of the sample means for a large sample size, it turns out that those are approximately normally distributed, even if the original variable isn't. This is one of the reasons why the normal distribution is so important, is that the means tend to follow a normal distribution as long as you take a decent sample size. And it doesn't have to be as big as you'd think. Like in our class, we're going to say as long as n is at least 30, as long as you've got 30 or more individuals in your sample, we can assume that the sample means are normal, even if the original variable isn't. So let's write that up similarly to how we did the first scenario. Consider all possible samples of size n taken from a population with mean mu and standard deviation sigma. Notice that this time we did not require that that population be normal. We just said we're taking samples from a population. The mean of the sample means will still be mu. So mu sub x bar is still equal to mu. That hasn't changed. The standard deviation of the sample means will be sigma divided by the square root of n. That also doesn't change. That doesn't depend on the shape of the distribution of the individuals. We're going to assume the distribution of the sample means will be normal provided that the sample size is at least 30. If the sample size is at least 30, we're going to apply this central limit theorem and say that the means are normal. If the sample size is under 30, then we can't make that assumption. Now, in real life, when people use this, the sample size that's required is dependent on the distribution of the original variable. If the original variable is kind of already mounded and symmetrical, but not a true bell curve, well, it takes a small sample size to get a normal distribution out of that. In our introductory course, we don't have the time to get that deep, so we're just going to set a boundary of 30. 30 or more and you're good. You can assume normality for the sample means, even if the original variable is not normally distributed. Let's look at an example. Historically, a certain medical procedure is completed in a mean time of 2.5 hours with a standard deviation of 1 hour. A random sample of 50 such procedures is collected. Find the probability that the mean time for these 50 cases is more than 3 hours. Okay, so you'll notice something's missing from this problem that we've seen in all of the other problems. It doesn't say that the variable is normally distributed. It just tells us the mean and the standard deviation. But the question isn't about the individuals. The question is about the mean time it takes for these 50 cases. We're looking at the mean of a sample. And so we want to look at the distribution of those sample means. And this is where that central limit theorem comes in. Our rule said that as long as we've got at least 30 individuals in our sample, we can assume normality. We're looking at the distribution of sample means from samples of size 50. 50 is bigger than 30. So because we've got a sample of size 50, we can assume normality. This is the distribution of the x bars, not of the individuals. The sample size is 50. I'm just going to note that off to the side to remind myself that I could satisfy the central limit theorem. That 50 is bigger than 30, and that's why I can draw a bell curve for the x bars, even though I couldn't do that for the individuals. That's the application of the central limit theorem. Going back to the problem, we see the mean of the individuals is 2.5 hours. And just like in the previous case, the mean of the means is equal to the mean of the population. So the number in the middle of this is going to be 2.5. The notation you would use here is mu sub x bar because we're looking at the distribution of the means, not the distribution of the individuals. We also need the standard deviation of the means, and we know that that's different than the standard deviation of the individuals. We divide the standard deviation of the individuals by the square root of the sample size. The standard deviation of the individuals was 1 hour, and the sample size is 50, so this is 1 divided by the square root of 50. Once we have these three features, we can use normal CDF to find probabilities. Once we get here, we're back in a case where we're comfortable. So let's review how we got here. The mean of the means is always equal to the mean of the population. The standard deviation of the means is always equal to the standard deviation of the population divided by the square root of the sample size. That was the same in our first example. What was different was that nowhere in this problem did it mention a normal distribution. But that doesn't matter when you're looking at the distribution of the means as long as you have a large sample size. And what constitutes large in our class? 30 or more. 30 or more is large enough to satisfy the central limit theorem. So that's how we knew this was a bell curve. Let's see what probability we're being asked to find. Find the probability that that mean is more than 3 hours. So 3 lives somewhere on the right here. We're going above that. So this is another 0.5 minus problem. 0.5 minus normal CDF. Left bound of 2.5, right bound of 3. Mean of 2.5, standard deviation 1 divided by the square root of 50. Again, I wouldn't bother coming up with a decimal approximation for that. You can just put 1 divided by the square root of 50 into your calculator. Now at first glance, that's only a half an hour difference, right? That's only 0.5 away. It seems like a small amount. But relative to the standard deviation, that's actually a pretty wide gap. You'll see that this probability is pretty small. Let's see how small. So 0.5 minus. Second vars, choice 2. Left bound of the area we're subtracting away is 2.5. Right bound of the area is 3. The mean of the distribution was 2.5. The standard deviation of this distribution is 1 divided by the square root of 50. Enter. And we see that this is actually so small it's in scientific notation. It's around 0.0002. That's 0.02%. So tenths, hundredths, thousandths, 10,000ths. That probability is around 2 in 10,000 or 1 in 5,000. It would be extremely unlikely that you could gather a random sample of 50 of these cases and have the average time be more than 3 hours. It just shouldn't happen. So here's how we use this in the real world. Suppose that they did gather a sample of 50 and they saw that the mean was bigger than 3 hours. or even equal to 3 hours, right? We use this probability to gauge how likely it would be that you could get a value that extreme, and we see it just shouldn't happen. So that means one of our assumptions is incorrect. If we actually witnessed a mean of 3 hours, and we know that the probability is very unlikely, then there is the off chance that we just had a weird sample, but much more likely is that either this mean is wrong or this standard deviation is wrong. And that's what we call testing a claim. So somebody might claim that the medical procedure is now going slower than it used to in the past, and they've got this evidence where the mean for 50 cases was 3 hours. And they argue, well, the math tells me that that shouldn't happen if the mean for all cases was 2.5 hours. So that mean is probably wrong. Or maybe the standard deviation is wrong. That's how this stuff gets applied. That's actually the kind of stuff we're going to do in Unit 3. I don't know if that gets you excited to learn Unit 3 or scares you away from Unit 3, but that's the kind of thing we're going to do in Unit 3 is test claims using probability. Okay, let's try another example. A specific brand of microwave has a mean useful life of 9 years with a standard deviation of 3 years. Find the probability that a randomly selected microwave of this brand lasts less than 5 years. Okay, so how do we proceed? Well, we try to find the Oh wait, it doesn't tell me the distribution of the variable. It doesn't say that it's normally distributed. And we're only talking about one microwave. That's not big enough to satisfy the central limit theorem. We can't do this problem. And if you want the reason why, it's because we don't know the distribution. Is this normally distributed? We don't know. And because we don't know that, we can't proceed with the problem. We don't know the shape. We can't just assume that this variable is normal. We weren't told that it's normal. Now you might feel like that's a trick question, but I wanted to demonstrate that we can't just do any problem using a bell curve. We can't do this one because we don't know that it's normally distributed. It doesn't say so. Let's look at a problem that seems very similar to this one, but we actually can do it because of the extra. Let's look at another problem that seems very similar, but we'll actually be able to do this one because we're looking at the distribution of the means and not the individuals. A specific brand of microwave has a mean useful life of 9 years with a standard deviation of 3 years. Find the probability that a random sample of 36 microwaves of this brand has a mean useful life less than 7 years. Now, at first glance, this seems to have the same problem we had before. It doesn't mention that this is a normally distributed variable, but we're not looking at the distribution of the individuals. We're looking at the distribution of the sample means because the question is to find the probability that a sample of 36 microwaves has a mean useful life less than 7 years. So we're not looking at the distribution of the individuals. We're looking at the distribution of the means for samples of size 36. And this is where the central limit theorem saves the day. The central limit theorem tells us that the distribution of the sample means will be normal provided that the sample size is greater than or equal to 30. Our sample size is 36, so we can assume a normal distribution even though the individuals were not normally distributed. The reason we couldn't do the trick question was that we were only talking about the individuals, and we don't know the distribution of the individuals. But for samples of size 36, the central limit theorem assures us that the means will be normally distributed. Now, we still need more information to be able to answer probability questions. We need to know the mean of the means, and we need to know the standard deviation of the means. But we have formulas for those. The mean of the means is equal to the mean of the population. The standard deviation of the means is equal to the standard deviation of the population divided by the square root of the sample size. The mean of the population is 9, so the mean of the sample means is also 9. The standard deviation of the population is 3, and the sample size is 36. So the standard deviation of the sample means is 3 divided by the square root of 36. And we could leave this as 3 over root 36, but this happens to simplify. The square root of 36 is 6, and 3/6 reduces to 1/2. And so I'm going to simplify that down, but you don't need to do that. You could just run with 3 over root 36. What probability were we being asked to find? Find the probability that the mean is less than 7. Okay, so 7 lives somewhere on the left here, and we're going less than that, so below 7. This is another 0.5 minus problem. We want to exclude this area right here. This is 0.5 minus normal CDF, 7 for the left bound of the area that we're excluding, 9 for the right bound of the area that we're excluding. The mean of the distribution goes in the third spot, so that's 9 again. And then our standard deviation for the sample means was 1/2 because the sample size is 36. Okay, now that's only a difference of 2 years, and that might seem like these bounds are close, but my picture is actually misleading. The standard deviation got reduced to 1/2 because of the large sample size. And so that's actually 4 standard deviations away from the mean. And this probability is going to be pretty small. How small? Let's see. 0.5 minus second vars, choice 2. The lower bound of the area we were subtracting away was 7. The upper bound was 9. The mean of the sample means was 9. The standard deviation of the sample means was 1/2. You could also type 3 divided by the square root of 36 there. Or you could use the decimal 0.5. Enter. And we get about 0.000317. Another very small probability, 0.003%. Right, so this could be another claim that's being tested. Suppose the company that makes these microwaves has claimed that their mean useful life is 9 years, but a consumer group samples 36 microwaves and sees that they only have a useful life of 7 years. What's the likelihood that they would last only 7 years? Well, the probability they last 7 years or less is only 0.00003. So it's very, very unlikely that a random sample would give us such a small sample mean. Much more likely is that one of our assumptions is wrong. Maybe that mean of 9 years isn't a correct value. That kind of claim testing is the kind of stuff that people do with this. Again, because we didn't know the distribution of the individuals, we couldn't answer this question about single microwaves. But the central limit theorem allows us to analyze this case because the sample size is so big. If I'd have picked a sample size of 10, like in our first example, we still wouldn't be able to do this problem because that's not large enough to satisfy the central limit theorem. I had to pick something that was at least 30 in order for us to be able to proceed. No more trick questions, by the way. I promise you I won't hit you with any more of those in this lecture. The scores on a stats quiz have a mean of 83 and a standard deviation of 12. Find the probability that a random sample of 100 quizzes has a mean score between 80 and 85. We don't know the distribution of this variable, and in fact it's probably not normally distributed. If it's graded on a standard scale where you're talking about a percentage out of 100, with a mean of 83 and a standard deviation of 12, a lot of that data is going to be bunched up on the high side. And so this is going to have what we call a skewed distribution. The distribution of the individuals probably isn't normal. But we don't need to focus on that anyway because we're not looking at the individuals. We're looking at a sample of size 100 and its mean. And so we need the distribution of the means, not the distribution of the individuals. The sample size that was taken was 100, so we can use the central limit theorem to assume normality. We've got the bell curve that we need. The mean of the individual scores was 83, so the mean of the means will also be 83. Mu sub x bar equals 83. The standard deviation of the sample means is the standard deviation of the population, which is 12, divided by the square root of the sample size. Square root of 100, the sample size was 100. This one also happens to simplify, so I'm going to do that. This simplifies to 1.2, or you could use 6/5, or you could just keep it as 12 over the square root of 100. You don't need to simplify it. Whether you simplify it or not, the calculator is going to give you the same answer. What are we being asked to find here? This is the probability that the mean is between 80 and 85. So here we have two bounds, 80 and 85, and we're finding the area between those. This isn't 0.5 plus or 0.5 minus. When you have two bounds, that's just straight up normal CDF. This is what normal CDF is built to do. Find the area between two bounds. The mean is 83. The standard deviation is 1.2. Now when you just look at the problem and it says find the probability that the mean's between 80 and 85, that's a small interval. So it might not seem like there's a lot of data in there. But when you look at the picture and see that the area encapsulates the mean, and when you remember that the standard deviation got reduced by a factor of 10 all the way down to 1.2, this is actually going to be a huge amount of area. Let's calculate it. Second vars, choice 2. Lower bound of 80, upper bound of 85. Mean of the means would be 83 because that's the mean of the population. Standard deviation of the means is only 1.2 because we divided by the square root of 100. And we get almost 95% of the area in there, 0.945, I guess 946 if I round up. So nearly all samples of size 100 would give you a mean in this range. It would be uncommon to get 100 of these quizzes selected at random and have a mean that wasn't between 80 and 85. Let's do one more. We'll go to a classic example. IQ scores are normally distributed with a mean of 100 and a standard deviation of 15. Find the probability that a random sample of 4 people has a mean IQ below 110. After all of these examples, this 4 is setting off alarm bells. Isn't that too small for the central limit theorem? It's only 4 individuals. You're right that it's too small for the central limit theorem, but that doesn't matter because we're told that the variable is normally distributed. Let's go back to the conditions that we used for our first example. If we know that the original population is normally distributed, then the sample means will be normally distributed. It doesn't matter what the sample size was. The first example we did had a sample size of 10, and we didn't flinch because we were told that the variable was normal. So it doesn't matter that the sample size is only 4. The distribution of the means is still a bell curve, even though the sample size is so small. I mean, think about it this way. If IQ scores are normally distributed, then that means for a sample size of 1, the variable is normally distributed. So if we take a sample size of 4, we'll still have a normal distribution. It'll just have a different standard deviation. That's what's going to be different. The mean of the means will be the same as the mean of the population, which is 100. The standard deviation of the means, however, will be slightly different. We have to take the standard deviation of the population and divide by the square root of the sample size. So sigma sub x bar is that standard deviation of 15 divided by the square root of 4. And again, I've got one that simplifies here. You could make that 7.5, it doesn't matter. So I know the sample size was small here, but that doesn't matter because we were told the variable was normal, so the sample means are automatically normal. The mean of the means is equal to the mean of the population. The standard deviation of the means is the standard deviation of the population divided by the square root of the sample size. We're being asked to find the probability that this random sample has a mean below 110. 110 lives somewhere to the right of 100, and we want to go below that. That's an entire half plus this piece right here. So this is a 0.5 plus problem. 0.5 plus normal CDF. The lower bound of the area that we need to add on starts at the mean. The upper bound of the area that we're adding on is the 110. The mean is 100. And the standard deviation is 15 over 2 or 7.5 or 15 divided by the square root of 4. Any of those will give you the same result. Okay, so 0.5 plus problem. 0.5 plus second vars, choice 2. Our lower bound was 100. Our upper bound was 110. Mean of 100. Standard deviation of 15 divided by 2. 15 divided by the square root of 4, 7.5. They all do the same thing. And we get a little over 90%. 90.9% if we round. I want to reiterate that this problem did not require the central limit theorem because we knew that the variable was normally distributed. That's why we could still approach it even with such a small sample size. If you're not told the variable is normally distributed, then you need a sample size of at least 30 to do this kind of analysis. This section has some pretty deep ideas and the problems aren't that easy, so if you have questions, please don't hesitate to contact me.